Okay. Okay, so after 1 week break, I'm glad to have Professor Nayana Majumdar as our speaker for the weekly colloquium series. And Professor Majumdar was born and brought up in the serene campus of Muography in Shantiniketan, where she did her schooling as well as bachelor's and master's. And then Professor Majumdar came to Shah Institute of Nuclear Physics for her PhD. And she also did a postdoc there and joined as a faculty member and has been there ever since. And now she's a senior professor there. And Professor Majumdar is an expert in various aspects of nuclear physics. And in recent years, she has been working on this tomography with cosmic muons, which she's going to talk about today.
ওকে, শুরুতে আমি দু চারটা বাংলা কথা বলতে চাইছি। মানে এরকম একটা স্বনামধন্য বিশিষ্ট ঐতিহ্যবাহী প্রতিষ্ঠানে আসার ফলে আমি যে কতটা ধন্য মনে করছি নিজেকে, সেটা প্রকাশ করার জন্য বাংলা ভাষাটা আমার মনে হচ্ছে শ্রেষ্ঠ আর কি। ইংরেজিতে ঠিক এক্সপ্রেস করা যায় না, বাট ওকে, if there is anybody who cannot follow Bengali, I can say what I just mentioned in Bengali, that I feel truly honored and privileged to speak about our research activities at Shah Institute of Nuclear Physics. And I express my thanks to the School of Astrophysics, especially Ritoban Chatana, for inviting me and giving me this opportunity. So the topic is muography with cosmic muons. So I will try to disseminate how this technique can be a very powerful tool to conduct non-destructive or non-invasive monitoring of any object on the path. And I will mostly try to keep it at the colloquium level, so I will not go into much technical details. Rather, I will try to tell a story, better story. Okay. So let us start from the very preliminary level, basic level. What is graphy? So according to a dictionary, it's a kind of visual representation. It indicates a form or process of writing, representing, etc. Or it can indicate any art or it's about the descriptive science. So it tells about the visual representation that makes some kind of images. So these are some examples of the graphies. You know all of them: photography, radiography, sonography, tomography, holography, like this. All these are some kind of visual representation of some information. So let us look at the methodology of this graphies. What happens? There must be a source. Then that source emits kind of radiation or particle which interact with the target object which we want to explore or investigate or monitor. So we use this source to interrogate this object, and this radiation or particle which is emitted from the source interacts with the object, and that information of the interaction is received by some sensor. And that sensor transmits the information received from the interaction which is represented in terms of some image. That is the basic methodology followed in all the graphics. In photography, there is a light source and one target object, a human being or somebody else or anything else. And we have camera, and this photons from the light source interacts this target object and produces some information which is produced as a photo. There are some sensors inside the camera unit. Similarly, in case of radiography, which you are all aware of in connection to hospitals, medical tests, etc., where there is external source, and this extra from the source interacts with some body parts, here in this case. And that interaction is, the information of that interaction is received on this plate, which is developed to produce an extra plate, to give you the information about, say, your foot or hand or whether there is any crack, fracture, etc. So there are lots of other source or particles which can be used for doing this type of imaging. Say neutrons also is there. For those particles, the choice of the source actually depends on the nature of the object and what kind of information we want to get from that object. Depending upon that, we choose the source. And all those sources can penetrate, let's say, maximum to 1 meter. But if we want to know or investigate a big, large object, for which any artificial source may be difficult to get. So muography, where the source is the cosmic muon, can be useful for such objects. And the muons have great penetration power that can be utilized for taking muography of some large object like a mountain, a temple, a big building, furnace, something. And this interaction of the muon with that object is read by some kind of sensors, which we normally call the muon detectors. And they produce this type of representative image. Okay. Depending upon what information they are processing, the image is produced on the basis of that. So this is the muography. Now the muography is performed with cosmic muons. Where does this cosmic muon come from? So we know about the primary cosmic rays, which are mostly the subatomic particles, 90% protons, and maybe 99% of alpha, and some the rest part is composed by some heavier nuclei where maximum iron can be did, or there are several more high energy, heavier nuclei, which are much less in proportion. And they travel through the interplanetary, interstellar, or even the intergalactic space with so tremendous speed, energy, etc. So these are called cosmic rays, primary cosmic rays, because there is no secondary cosmic rays. That's why the name is given to this cosmic rays, which travel in these spaces, are called primary cosmic rays. And these cosmic rays may originate from sun. Usually the lowest energy cosmic rays are they originate from the sun, which are called solar cosmic rays or SCL. And the comparatively heavier cosmic rays, they are produced inside the galaxy, Milky Way galaxy.
By heavier, you mean more energetic?
More energetic. Yes. And the highest energy particles, the cosmic rays, they come from distant galaxies. So they are called extragalactic cosmic rays. So this source of the GCR are mostly supernova or their remnants. And this ECR are proposed to be generated from the intergalactic shocks and so on. Anyway, so this is the kind of the energy spectrum of the primary Bose matrix, which you are maybe all aware of this or familiar with this type of spectrum. And this can have energy roughly from 1 GeV to 10 to the power 8 TeV per particle, and it follows a forward law approximately. Now, this primary cosmic rays, when they enter the atmosphere of the Earth, they interact with the atmospheric molecules. And then these cascades of hadrons are produced, in which the pions and kaons are mostly abundant. So the dominant decay mode of the most abundantly produced charged hadrons, which are pions and kaons, they produce leptons. These are the decay channels. And the vast majority in a cosmic shower are the muons, which reach up to the Earth surface. So muons are actually the secondary cosmic particles. They are produced 15-16 above the sea level, that means at the upper atmosphere. So how they could reach the surface of the Earth? Also, they are very unstable. They have a mean lifetime of around 2.2 microseconds. So they can reach the sea level due to the relativistic time dilation. And since they are not hadron, they are insensitive to strong nuclear interaction. They are only subject to electromagnetic interaction because they are charged, which is Bremsstrahlung, but their mass is much larger with respect to the electron. So the Bremsstrahlung is proportional to 1 by m squared. That is why the probability is very big. So the energy loss mechanism only involves the ionization excitation produced by this muons when they pass through any matter. So let us look at the interaction of muons with matter. So this is matter and the muon is incident upon the matter. There may be two types of collision, of which the inelastic collision is more probable, where it collide with the atomic electrons. And due to this collision, two types of products can be generated. One is this, due to the collision, the muon transfers its energy to the atomic electrons and raises it to some higher excited levels. So this gives kind of excitation of the matter, atom of the matter. And it gives rise to excited atom. So this is one way of using the energy of muons. The other way is that it can generate ionization. It can knock out the electrons from the atoms, which gives rise to ion pair. And sometimes if the collision is, depending upon the proximity, the collision may be hard enough, from which the electron can get large amount of energy, which emits as a delta ray, which can further cause further ionization, etc. These are called delta ray rays. So this is where the muon loses its energy. But in elastic collision with atomic nuclei, which is also dependent upon the proximity, there is no loss of energy, only the muon gets scattered. So this cause the scattered muons can have when they pass through the matter. Now, utilizing these two interaction methods, these imaging technique has been, these two imaging techniques have been developed. One is muon absorption or transmission tomography, where the muon interacts with the matter using its inelastic collision. So it relies on the absorption of muons in the target matter because the muon loses its energy and eventually it gets absorbed in the matter. So this is the absorption of muons which can give rise to this muon absorption tomography. This tomography method is suitable for actually very large object because there is lots of matter. So there is a possibility that muon will get absorbed inside it through multiple interactions. And the other tomography method is muon scattering tomography. It relies on the scattering of muons in the target matter. And these scattering methods are suited for usually interrogating small or medium-sized targets. Now, these two types of transmission tomography methods refer to different types of detector configuration, etc. For muon absorption or transmission tomography, only one layer of detector is good enough because that will see whether the muon is reaching the detector or not. Comparing it with the open sky flux, the detector information can be analyzed to know whether some muons are absorbed within the matter or not. But in case of scattering, you have to know the deflection of the caused by the interaction. So you need two layers of detectors. The upper layers will give you the information on the incident trajectory, and the lower detector will provide the information on the scattered trajectory. So from these two trajectories, you will be able to know the deflection or scattering. And the advantage of this tomography technique is that this is uniquely sensitive to atomic number because this deflection is dependent upon the atomic number of the matter. So from here, you can identify the matter by studying the image, tomography image. From here, you cannot because it gives you only the shape or maybe the size of the object, but not the matter properties. But from here, you will be able to know which material is this one. Okay. There are also advantages as well as disadvantages of this imaging technique. The major advantages are that it's a natural source of radiation and it's available at no cost. Whereas the other sources you have to spend some money to get.
Like other sources, right?
Like X-ray, like neutron source, etc. Okay. And there is no radiation hazard involved because we are always having
Muons.
Yes. And the radius, one muon is passing through your fingertip in a minute.
In a
At this
minute.
rate, in a minute. Okay. And the additional advantages, it has a large range of penetration to upper atmosphere to even underground. So it may be useful for scanning the big static objects. There are disadvantages of course. It's a slow process to acquire large statistics. You cannot control the flux rate, etc. So it's constant flux rate. You cannot increase it to complete your imaging in a time scheduled way. Okay. Another thing is that there is a dependence on muon momentum, which is not usually measured on an individual basis. And this muon momentum has uncertainties. So that always contributes in some way in your imaging. And there are reciprocal challenges posed by muon interactions. Suppose in absorption images, there must be some muon scattering which smears the absorption image. In case of scattering image, the depletion of statistics through absorption of the muons in that. So every technique has its pros and cons.
So just a quick question. Is
Yeah.
it possible that some muons will come from underground from the other side of the earth by penetrating from the other side?
That may happen for neutrinos, for
But not
muons.
Definitely, yeah.
For muons, it's not. Yeah.
The muons are 1 kilometer maximum that you go in.
Yeah, yeah. That
So the
500 meter or 1 kilometer, you can get some muons.
So we-
Very good.
Okay, so let us see closely the muon absorption or transmission tomography. This is the historically first technique to be exploited for imaging with cosmic muons in 1950s. And it was used to measure the overburden of a tunnel. So it was easy that the detectors could be placed just inside the tunnel, and it measured the incoming flux of the muons. And by comparing the flux with the open sky flux, the matter content of the tunnel or the composition structure of the tunnel would be investigated. Next, in 1960s, the muon transmission imaging was used in the pyramid of Giza to search for some hidden chambers. But unfortunately, no hidden chamber was found. But there was an effort. But in Scan Pyramid project mission, a big void was found in 2017. Okay, I will come to this later.
There will be more funding after this.
Okay, so this was the beginning of muon tomography.
Seems like neon things and Egyptian pyramids have a strong
Strong.
connection.
Yeah. Okay. So in muon absorption and transmission tomography, the muon flux which arrives at the muon detector is compared to free sky flux to determine the probability of muon absorption along a line of sight which determines the opacity of the target. For known target dimension, this opacity can lead to average density measurement. Or vice versa, if the density is known, the target shape or dimension can be determined from this opacity. And the statistical precision, these are some mathematical detail where it depends upon the number of observed muons. Okay.
Just as a little clarification.
Yeah.
In the image, what you were seeing that they are coming as if some inclined angle, right?
Yeah.
But that's not
From the top.
always in the
Yes.
top.
For these cases, for the pyramid or other some structure, you cannot put the detectors inside. For tunnel, it is possible. So for these pyramid or temple or some structures like this, you have to place the detector on one side and you have to analyze the inclined flux, muon flux,
That is very, very less compared
Yes,
to the.
compared to the. So the time will be taken.
But
For
one
this.
question.
Yeah.
How can we control whether it is an elastic or an elastic process that is going on? Because we cannot control whether the matter is getting.
Yeah, both are taking place here.
Okay, so the detector contains both the processes, I mean the detection facilities.
Yes, but for scattering, the elastic collision will give rise to scattering.
Yes.
But to know the scattering, you have to know the incoming trajectories.
Yes.
You have no way to measure those incoming trajectories.
So from
You can only get the incoming flux from some simulation or like that.
yes.
Okay. And what flux you are getting here, you can compare it with that simulated flux. From there, you can know whether there is a difference between these two fluxes that will give you the information about the target in between. Okay, I will come to more detail in this relation. Okay, now let us come to muon scattering tomography, which is comparatively newer technique. And it was proposed in 2003 only. Almost after 50 years or so, 60 years after the muon absorption technique. And it was proposed that this scattering technique can be utilized for identification of metrics. So this was published in Nature, and they investigated a small experimental setup which contained a tungsten cylinder supported by a plastic plate, which is not seen in the image, and this tungsten cylinder was supported by two steel beams or steel rods. So this is the experimental image they obtained using the muon scattering tomography, using detectors on both sides of the experimental setup. And this was a simulated one. So by comparing, you can understand that the experiment was quite accurate and give proper information about this. So this scattering tomography has the ability to reconstruct complex objects. And it has the ability to detect dense materials of high atomic number hidden in a much larger volume of material of low atomic number. So plastic material is not safe. Only since these are steel, they are relatively higher atomic number, so they get detected. But the density of the tungsten, you can see, which is the contrast is much higher than the others. So
what is actually the dimension of these steel or the tungsten?
yeah, this one was maybe around 5 centimeter dia or like that, as far as I know.
And it took time.
Is to more scattering rather than light element.
Exactly. So this is like your the answer here. You can see the answer. The muon scattering tomography depends upon this type of formulation. Actually, the probability distribution of the angular deflection of the muons, which is suffered by Coulomb scattering. In the probability distribution of angular diffraction in the Coulomb scattering of a charged particle by traversing matter, we know from the Rutherford's law, it's proportional to this. This is the first formulation. So after traversing a macroscopic amount of the material, the actual distribution features an approximately Gaussian distribution. It is followed from central limit theorem. That tells that if you take many have large statistics, that leads to a bell-shaped distribution. And it asymptotically reaches Rutherford's law in the tens due to rare large scattering events. Yeah. So this Gaussian approximation describes 98% of the actual distribution in a broad range of Z, and for not very thin targets, it's standard deviation of this. And if you look at this, this is the radiation length, and this x is actually the distance traversed by the muon inside the matter. And this radiation length is proportional to the Z of the matter. So in that way, this sigma is directly related to this Z. So if your Z is high, your deflection will also be high. Right? So the root mean square of the deflection angle is directly related to Z. So for heavier element, you can expect large scattering. And for low Z materials, you can expect small scattering. So this method is practically suitable for application where contrast is sought between a high Z and low Z materials. So in muon scattering tomography, you have to have two sets of detectors. One is for measuring the incident trajectories, and the other set is meant for measuring the outgoing trajectories. And the track reconstruction is to be done using the muon heat information obtained from these tracking devices on either side of the objects. It also depends upon the number of the muons. Okay, let us look at some famous global examples. There's some fascinating stories out there about this application of these methods. Okay, this is one example of the muon absorption tomography. Here, the Pfuffer's pyramid at Giza was scanned using several sets of detectors. One is nuclear emulsion detectors, and here is a horoscope made of scintillation detectors. They were placed somewhere here. This is the Pfuffer pyramid. And there are three chambers known. One is king's chamber, another one is queen's chamber, and there is a subterranean chamber. And these chambers are connected by a grand gallery. So these are all known cavities or chambers in the Pfuffer's pyramid. Okay, and another detector was employed here, which is a kind of gaseous detectors, micromegas detectors. And this whole project was carried out by two countries, Japan and France. So these two detectors were commissioned by Japan, and this one was commissioned by France. Okay, so these are the images they have obtained with different detector sets. So this anyone, yes, this 2D histogram of the detected muon flux kept it here. And by comparing with simulation, which includes the known structures of these three chambers, etc., and also the grand gallery, a muon excess could be observed, which indicated that there is something unknown, something hidden there, some hidden void. That's why there is a rise in the muon flux, because there is lack of material. That's why the rise in the muon flux was observed. Similar thing was observed in H1 also. They also compared with the simulated one and observed the muon rise in the muon flux. Here you can see all these known chambers are marked. This is actually the unknown void, and this is a known part B. This is also known. This is also known. These are all known. This was the unknown part which gave rise to this excess in the muon flux. Also, at the they observed, you can see from here, I hope, that there is a small peak here. There is a rise in the muon. So all these results indicated that there is something, some void is there which was unknown. So actually, this was a discovery of a hidden chamber using this muon absorption tomography.
So, but that chamber was not connected through this
No.
grand gallery
No.
or something like that.
Even the
Did they
archaeological department didn't have any information about this.
But then, did they actually then confirm by
Yes,
going
later the archaeological department, they sent some robots or something, did something. Still, it's not open for the tourists, but it's there. It's an accepted fact.
Was there anything interesting there?
It's not open,
At
so I don't
least
know.
they did not
At least
tell
there
us.
is no public information.
Maybe they were aliens.
Okay. So another global example of civil engineering is that this was done in Alfreton Old Railway Tunnel in UK. So there were several Victorian age railway tunnels in the UK. And while building this tunnel, usually some shafts were used to for circulation of air or transmission of materials, transportation of materials, etc. Later, those shafts were covered from the tunnel side as well as from the top side. So for this railway tunnel, they have the information of only these three tunnels. So these three tunnels are known. So after carrying out the muon absorption tomography inside the tunnel, a muon excess was observed here, which was not recorded in their civil engineering document. And later also they confirmed that yes, indeed, there was a shaft which was covered from the tunnel side as well as from the top side, so it was not visible and unknown to the engineering department. And it could have caused some type of accident or something. That's why they requested this probe to conduct a survey.
What are the other peaks for other tunnels, 3 tunnels?
These 3 tunnels, because they have corrected for those peaks. So, yes. So they wanted to say whether there is any excess muons beyond that. Okay. And this is some close-ups. This is the unknown part where you can see clearly a muon excess. And this was a 2D histogram generated to see the size of the dimension of the cavity. So this is another success story published here. Okay.
This is also reset.
This is also, these are all presents. Often, this is a very well-known thing that Fukushima Daiichi reactor had some kind of explosion inside the reactor due to the tsunami. And this is actually purely a simulation work. They tried to study whether it is possible to know or scan the core of the reactor using either of scattering tomography or transmission tomography. So this was published in Physical Review Letters. So this is a model, okay, the simulation model where they considered the reactor core, and this is the reactor. This was a pressure vessel, and this is the core, and they actually modeled 3 conditions. One is that the core is intact. In other case, the core with 1 meter diameter material removed. From here, it is removed and placed just below here. And there is no hole. These 3 models they produced and simulated using the muon scattering tomography as well as muon absorption. And these are the results. This is for, can you see, this is possibly 1 hour. This is some 10 hours. The resolution is not very good.
The top bottom left says 4 days.
4 days, and this is
6 weeks.
Yeah. These are hours in terms of hours. So this is the empty core. This is the intact core, and this is the void core, means one small portion from here and put there. So here you cannot tell anything from these images. But if you come to these 4 days, you can see in the scattering tomography, you can at least see the core. And for transmission tomography, you cannot see. That is why the muon scattering tomography is used for this small and identifying the material in small cases where the identification of material is necessary. And muon absorption tomography is not that successful because the uranium fuel and water are more or less similar. So they will produce similar kind of absorption. Only the scattering can give you some information depending upon the scattering angle that those 2 materials are different. So that is why scattering technique was more successful. And you can see in 6 weeks data, you can see a void here and a small material here. If you increase the exposure to maybe say more than 2 months or more, so maybe it will come distinctly. So in that way, they compared these 2 techniques and proved that for imaging of this Fukushima Daiichi reactor core, muon scattering tomography will be more suitable.
What did you say are equal for water and uranium fuel?
Uranium fuel is also a liquid fuel.
Oh, okay. So here the atomic number doesn't matter.
Doesn't matter in case of absorption.
Right.
Only scattering can give you some information about the material properties.
So for absorption, what matters is density.
So if you want to know whether there is any void or the shape of the, say, I mean, the pyramid or something is there inside a big temple, then you have to rely upon the absorption technique. Their scattering will be difficult because you have to put detectors on either side. You cannot put one side detector at one side of the pyramid and the detector on the other side of the pyramid. That will be difficult and run these both set of detectors. Okay, this is the global example of security applications. This is purely a case of muon scattering based tomography. So this is a discovery portal monitor test at US and Mexico border to inspect the contraband items used in the cargo, different cargos. And you can see this is a package where the guns are hidden inside the packaged water bottles. So by muon scattering tomography, this guns were detected. And here, this is there is a small video. This was produced by muon scattering tomography. That these are some spools of steel spools. Using the X-ray, the spools, there are some voids you can see in between the spools. And some drugs were hidden there. X-ray imaging could not reveal that there is a kind of hollow space inside the spool and the drugs are hidden there. So only muon scattering tomography, it showed that there is something is there with low density. Something is there, it indicates. So after that, they opened the cargo and found that there are drugs. So these are the, I mean,
These images, how long is it?
okay, so this was for, as far as I remember, I forgot to mention the exposures. Maybe it was 5 hours or 6 hours like that.
But the X-ray will be quicker.
It's really quicker, but it could not reveal the secret things. Okay. So let us look inside the MS. So I once again repeat these relations where the radiation length depends upon the set of the number of the ventral. And by measuring the deflection, you can reveal the information of the materials. So you can see here, the iron will produce a small scattering in comparison to uranium. Yeah. So in MST, that is muon scattering tomography, the reconstruction of incident and scattered muon trajectories will be made by using two sets of upstream and downstream detectors. And the trajectories are approximated as straight lines. And the determination of scattering through extrapolation of both trajectories within the object volume in 3D, which are usually divided into voxels or 3D volume segmentation. And there are several methods for this, finding this vertex points, scattering vertex. Point of closest approach or POCA is the most popular one because it's very simple, but it's quite effective. There is a more complicated one, a computationally intensive algorithm, bin cluster algorithm. And there are maximum likelihood expectation minimization MLEM methods and several other methods which can be used to get the scattering vertex. The point of closest approach is a very simple but fairly effective imaging method. And it assumes that each muon scatters only once within the target volume. While it is not actually not the actual case in reality, because the muon suffers multiple of scatterings. So, but it approximates that only one point is there where the muon scatter. The muon trajectory is measured by the two trackers and extrapolated up to their point of closest approach. Not necessarily they will intersect, but the distance between the closest approach, the middle point of their closest approach is considered as the scattering vortex. So the foci is at the middle of the line of the closest approach. Albeit somewhat crude, the single scattering approximation yields quite good results in many cases, especially in smaller objects. Then the next thing, the important thing is instrumentation of muon trackers. So muon trackers may be three types. Scintillation detectors may be used. Gases detectors may be used. Emulsion detectors also may be used. These have their own pros and cons. Like scintillation detectors, here the atoms in scintillators emit light, and these lights can be collected by the photomultiplier device, which will convert the light signal to electronic signal, and it yields information on the amount of energy released by the impinging particle. And for gaseous detectors, here the charged particle will produce a trail of electron-ion pairs when it passes through the gas volume. And these electrons and ions are collected by application of electric field. And also, they can offer quite good spatial resolution, few tens of microns. And large area coverage can be achieved often at affordable price. That is the good thing about it. Emulsion detectors are quite old detectors, old technology. Here the resolution is determined by the size of the emulsion grain, but very specific equipment is needed to analyze the nuclear emulsion plates. You have to analyze the plates to develop the information. So these are some detectors which are used in case of MST. Like these are the straw tubes. These are multi-wire proportional counters. This is RPC. These are all gaseous detectors, and these are new generation gaseous detectors where you can get the position resolution of the order of a few tens of microns. Okay. And these scintillators can be used for getting the good spatial resolution, but you have to design or machine the scintillators accordingly. And the recent use of the SIPM has interest to use the scintillators in the MST. Okay. So electronics, I'm not going to much detail. Electronics, front-end electronics is another requirement in MST instrumentation. It is quite relaxed as a high gain is achieved in gaseous detectors. And so it leads to simpler design and reduced cost for electronics. Obviously, the muon flux rate is much lower than like LHC, etc. So the fact development should be there along with the detector fabrication, and using all this setup, you can prepare the data using your data acquisition, and you develop the image processing protocols to analyze the results. And to generate the muon flux, you have to rely upon some generators. And these are the simulation part which can be used to optimize the design of this MST setup. The performance of the setup can be reproduced using the simulation, and depending upon the result of the simulation, you can fine-tune your design of the setup. So based on these scopes, some R&D efforts are currently ongoing at SIMB. So we have identified an application area, that inspection of civil structure and nuclear waste, to utilize the muon scattering tomography for this investigations. And it leads to the development of prototype MST setup for material discrimination. And this comprises of three different sets of R&D sector. One is numerical simulation. Here the muon flux will be generated using Fry or something. The reconstruction of muon incident and scattered muon trajectories, then scattering vortex determination using POCA or BCA, then image reconstruction and analysis, and optimization of the design parameters on the basis of simulated results. In the instrumentation, design and fabrication of detectors is an important part where RPC, GM, TGM, SIP, and this type of detectors can be used. And testing of these detectors for their performance, optimization of their design and their performance using simulation, and the development of electronics and the data acquisition. And finally, the image processing part, where we have developed a pattern recognition method for material identification, as well as we have tried machine learning, tried to apply machine learning techniques to extract useful information. And the development of analysis protocol combining these techniques is underway. So I will go through quickly some salient results of our R&D efforts at SIMB. This is the numerical simulation conducted for this MST setup using 6 gaseous detectors, 3 in the upstream configuration and 3 in the downstream. And this you can see, but if you want to, if the scattering vortex is determined by the POCA using the resolution, ideal resolution of the detector, there are 3 blocks. One is lead, one is uranium, one is aluminum. These 3 were there. But if we use 1 centimeter resolution, you cannot distinguish between these metals. Okay. And if you use BCA, this is the beam cluster algorithm, which is quite sophisticated one. Here you can see that ideal resolution, they are more or less similar, but when a 1 centimeter resolution is applied for the detector, the outcome of BCA is much better than POCA. So BCA is in that way more preferable. Okay, so instrumentation part, we have constructed glass RPCs and conducted the simulation to see the electric field configuration in the detector depending upon the components used for making the detector. This is the electric field configuration. These are the simulated current density through the side and button spacer of the RPC. And depending upon these, the ratio between the resistivity of the button and the electrode was determined. And this is the potential measurement of RPC electrodes and simulated potential distribution at different surface resistivity. If this is actually the graphite coated electrode, yeah, depending upon the coating mechanism, the surface resistivity can differ. So the potential distribution can also differ with the distribution of potential distribution can also differ with the graphite quality of graphite coating. So that is also simulated here. So in the next, some readout scheme was developed for reading the signals from the RPC. And this readout scheme was based on the Nino assay. It was actually produced by Alice collaboration. And another FPGA-based backend electronics, which was purely developed at SIMP. And using this data acquisition scheme, the signal from one single RPC was taken. And this is a kind of a muon absorption spectrum for a lead block placed over the RPC. So you can see when the block was placed here, this was the spectrum we obtained using this scheme. And the block was moved towards the side of the detector, and this was the spectrum. And it was compared with the simulated images, which are quite closely agreeing. The other for other detector options, we have procured some detectors from SIR. These are new generation detector components, which have been assembled at SIMP and used for the R&D. This is GEM and this is TGEM. And these are the heat map, gain map measured for the GEM. And for TGEM, the gain variation with time was also measured. these are all the products from CERN, and later we decided that whether we can produce some of them at India. So we chose thick gem detector, which is comparatively should be comparatively easier to fabricate in comparison to the thin gem detectors. So these detectors were produced from one of the Indian fabs, and this is the comparison between the CERN detector performance and the India-made detector performance, which are quite competitive. And in our future plans, we have plans to use double thick gem to increase the effective gain and increase the dimension of the detector, and integrate with the existing FPGA-based data acquisition, which is still pending. And we are also working on developing some SIPM prototypes. Okay, so, and the last part is the image processing algorithms we have developed at SIMP. This was analysis protocol using a pattern recognition method was developed for 2D image. Actually, it's a projected image. We are working on right now the 3D image. This is the image of the 3D scattering vertex map, which is actually projected on the central plane. So it produces a 2D projected image. And this is actually the simulated 2D images produced for different detector resolution. This is for 500 micron, and this is for 200 micron. And in this pattern recognition method, a filter was designed. Suppose for this case, a filter was designed which could identify the iron. The middle block was iron, and the materials higher than with higher Z than the iron. So it actually eliminated this one, which was aluminium, and the other materials were possibly one was zinc, another one was lead, and another one was uranium. All of them were detected using this pattern recognition. And if we use the lead filter, only the lead and the uranium were detected. Other materials were discarded. And this results, this is the application of the same technique, same algorithm or pattern recognition method in identifying. This is the lead block inside a iron box, whether they can identify the lead. And this is the iron cylinder, lead cylinder inside an iron box. So this pattern recognition method would identify both the cases. Whereas DB-scan is another neighborhood algorithm which could not perform could not perform successfully or satisfactorily, I should say, to get to the shapes of the disc shapes. This is a square one and this is a circular one. For DB-scan, it is not getting the actual shapes. So in that way, that PRM method was very successful, and that method was applied to process the images for civil structures. This is a kind of rusted iron bar inside a concrete structure. And after application of PRM, then the rusted river could be imaged in this way. And this is a concrete filled steel tube where there is a void. And after processing of PRM, this image could be achieved. And these are some voids in the concrete there, and PRM produced this kind of analyzed result. So these are the results of the application of this filtering method in the civil structures. And recently we developed a ML technique, which is support vector machine based, that was used for the classification of materials. Support vector machine is a model which draws a decision boundary between two classes. And the dimension of the hyperplane depends upon the number of features. Suppose this is just a line when the hyperplane is r to the power 2, and if the hyperplane is r to the power 3, then the hyperplane is actually a plane. For the MST, it is trained with the scattering vertex density and the average scattering angle for each pixel of the image. So in our case, the hyperplane will be like this. So this was applied for image processing of nuclear waste. So this is a case of nuclear waste drum filled with uranium, lead, stainless steel, and air columns. And this was the image produced by the 70 micron detector with 70 micron resolution. And this is the image produced by the detectors with 5 resolution. You can see the difference between them. And their column height is 30 centimeter and muon exposure was 2 days. And this is the case, same case. This is 75 with 70 micron resolution, and this is 500 micron resolution, but the column height is smaller. This is 10 centimeter, and so the muon exposure was much larger. It was 7 days. And after applying the SVM, you can see the difference between SVM hydroplates between this different classification after classification of different materials like air, stainless steels, concrete, and the lead. And this represents the confusion matrix of this case when the height of the columns was 30 centimeter and exposure was 2 days and resolution was 70 micron. And this was the confusion matrix when the height was 10 centimeters. So these two things were obtained by using this machine learning technique. So these are the challenges for the time being. For MST, the slow, it's a kind of slow process to acquire large statistics because it comes at a constant flux, constant rate. And it has a dependence on the muon momentum, which cannot be measured usually on individual basis. And there are reciprocal challenges, as I mentioned earlier. And the important thing is that still the R&D sector lacks infrastructural support to build this type of systems. And working relationship between the R&D sector and the industry is very weak, which poses challenges in building MST setup for societal application. So these are the real practical problems we are facing now, and we are struggling to produce a kind of MST setup. So these are all lab activities, some photographs, and these are the publication related to only the MST. We have working from say 2015 or 16 like that, and these are the outcome. This activities. Huh? Shukridar, old photo. Shukridar, Sandeep. এটা অনেক প্রথম দিকের, এটা অনেক পরের দিকের ছবি। And they are the key players, the workforce behind the MST. Dr. Sridhar, Vishal, Pramita, Shovendu. They are all now postdoctoral or in permanent positions. And these two guys are continuing their work. One of them is here, Shubhabrata. And they are the backstage supporters. Pralay is one of them. So his work is also supporting our activities. Okay, so that's all for the time being. Too many information.
Okay, questions?
Yes, please.
Yes.
Since we are using two detectors,
Yeah.
one is the first and then second, in the middle is the material. So if the particle passes to the first detector, it will has to be scattered somehow. If it doesn't scatter, we won't track it. So if it scatters, then again it passes through a material and then again it reaches a detector.
It scatters inside the material.
It scatters with the material, but
Okay.
somehow we are tracking it using two detectors, right? If a detector tracks a particle, that means some interaction is happening. If the interactions are happening at the first detector, then some of the flux will or the energy will reduce or something will happen. So
That in case that we have some time tag between. Okay, so we can identify this is the muon which is interacting in the first detector as well as in the second detector. So you have to tag these two events so that you know that they're coming from a single point.
but the muon will go through the material and it will scatter to a different angle. Then how will
How are you tracking the muon, same muon between the detectors while it's going through the material because you have no idea of what is.
So in the detector, it's not really changing directions.
Yeah.
Yes.
Material in between, so during scan.
It's like in gamma ray, you were just describing Fermi lab, right? Fermi lab is doing the same thing.
Right. So wherever the muon passes, it gives you the position information. Okay. So it comes through this detector, right? Then there is an object.
Yes.
Okay. Then it scatters. Then enter another detector. So here also you get some position. Actually, there are multiple detectors so that you can build from each of these detectors, you will get a set of XY information. Say from here X1, Y1, this is from X2, Y2. And using all this information, you can reconstruct the full track.
What I am asking is that if it goes to so many detectors, a lot of flux will be lost.
No, no. Because in here, these are mostly the gaseous detectors. So it will lose no energy in the gas. Otherwise, it would have lose its energy in the atmosphere also.
The low
Okay,
scattering takes
it,
place.
it will lose energy actually through ionization and excitation, and that will be we will get information XY information from those things.
And is it using the brainstorm radiation method to kind
Brainstorming you cannot expect from muons
of
because muons have very large mass,
okay.
right? Yeah, do massive. So from here, if you extend the track here, and from here you extend the track here. So you will get either you get some intersection between them or in the closest approach line from which you will get this from the center you will get the foci, and that will be considered as the scattering vertex. Otherwise, if they intersect, this intersection point will be considered as the vertex. And from there you will be able to know them actually. That will
Okay.
give you the information.
Other questions?
Metric. Right, that should be a question.
Is there any medical sessions?
No, muon tomography medical application is difficult because muon won't interact with human flesh or body or
It pass-
bone.
they won't
It will
change.
pass because it is passing through me and you every time. So no change.
Yes, my question was related to this. So,
Yeah.
what is the typical atomic number or the typical element that we can detect with the modern day detector? So, is it like iron and heavier, or what is the
Oh
threshold?
well, it's a good question. Usually, I don't have the result. We could, by applying the machine learning method, we could differentiate between the air and minimum iron possibly. Okay. I think at least 10 or 20 Z difference between the Z number should be there to detect those or identify those materials with the presently available resolution of the detector. As far as I remember, if I remember the numbers correctly. But it may be difficult depending upon the detector resolution.
Another question. So, since you're talking about civil applications, so I don't remember all the detector types you were talking
Is
about.
correct. Yeah, is correct.
But what would be like the monetary aspect? Like how expensive are these detectors? Because you would probably want a lot of them to actually do and.
Okay, that is also a very pertinent question because making for civil structure you have to make large area detectors. Okay, so in that case you will always try to go for cheaper ones. Cheaper detectors are there like RPC detectors which you can make from the materials available in the market, right? So that detectors can be made, but you have to have that much infrastructural support or engineering support to make these large detectors. That is the main problem with our country or our present scenario. Yes. So we can do only lab test for the time being, and real field application is quite challenging then. In that sense, yes.
You showed, you told us about the drug detection and all those things. That means there are portable detectors, right? So I'm asking, you told us about detectors, but what about the transmitters? I mean, sources are only the cosmic units, right? We cannot produce any local sources and then detect all this.
Yeah, that's the main.
Local sources, yes. There are some muon generators. There are some areas where they are planning to produce muon generators, etc. But that also costs something for in comparison to naturally available muons. There are also disadvantages of using local muons. They are constant. They are fixed, and the flux rate is constant. You have to wait for say 10 hours.
Things that can be actually detected.
Yes.
Economic areas. So that means there are large amount of flux is coming.
Yes.
Which is.
Yes, but the flux rate is constant, so you have to wait for maybe say 10 hours or 7 hours at a port when the trucks are passing. You cannot detain a truck for 10 hours to be scanned or implemented.
Yes, that's what I was also thinking.
Yeah, that is a
You can't
real
ask
problem.
the, I mean.
Or the sheet.
No,
metal
but
that is-
there are other questions here. One hand, you cannot tell them to wait for too long. On the other hand, waiting is still okay, but searching for something without any prior cause is not allowed at all. So you have to first get some prior cause to search it. Now all rules are being broken, by the way, in the US, but that was the thing. So for that, detaining is okay still, but you cannot get into it without having any cause. So that can provide you the cause.
What
So-
kind of materials are suitable for this?
What's suitable for?
For what?
The detectors.
For detect-
For detectors, there are several types of detectors. Gas detectors is the cheapest one.
Gas, what?
So gas that normally used is argon.
Usually
with
inert gas.
inert gases. Argon. Okay, so there are scintillators as well, but scintillators are difficult to get very good resolution in the scintillators because you have to machine the scintillators in a very fine way, and because scintillators doesn't have, I mean, the position information capabilities or readout kind of thing. So you have to machine the scintillators very accurately, very
Because it's
finely.
emitting light and then.
Yes, only the light information you can get from one unit. So that will give you the information of that position. So you have to make the units very small units.
One last small thing.
Yeah.
You showed pyramids.
Mhm.
So Giza pyramids before that, and also you showed the sun pyramid, I think, Mexico.
Yeah.
Sun pyramid. So you told us that there is some kind of vacuum or space inside the
Yes,
Giza one, but what about the sun pyramid?
There was nothing.
There's nothing.
Nothing.
Testing happened.
Yes. The SSR has a question for a long time.
Look, what decides the resolution of these detectors?
What this is the resolution of the detectors. Okay. That depends. There are lots of things. In case of gaseous detectors, the kind of readout structures you take for to take the electronic signals out. That decides one part. Another one is the configuration of the detector, how the electrons are generated, how they are multiplied, how they are focused towards the readout plate. There are lots of small internal dynamics that decides the resolution. Roughly bolte gele just S by root over 12. That is the strip pitch. This is a rough formula we use. The strip pitch readout strip divided by root over 12. That gives you the.
Well, I was not asking about particularly the detector resolution. I was asking how the structure you are
Yes,
deciding.
yes, that will depend upon the configuration, how separated your detector layers are, how big they are, your acceptance is how much, and along with that, the detector resolution. Combining all this, you have to decide the angular resolution of your scattering setup or absorption setup.
And that also depends on your how good your simulation is.
Yes. That's why we do normally simulation beforehand to know whether our setup is giving us the desired results or not. Accordingly, we change or fine tune the other parameters, design parameters. So simulation is very necessary for this before building a big one.
Other questions? So I had a quick question. So you were showing some 2D through 3D, 3D to 2D information. But the way you described how this works, either scattering or absorption, it seemed to me that we are getting 2D information. That is, the entire thing is being
Yes.
projected on one plane.
Yes.
So
This
to
is
get
the
3D,
problem.
you have to put detectors in multiple positions. Is that right? Or if you want to get
No.
3D information, what do you do?
3D information we are also trying to get actually for simplification of our computation we have for the time being opted for 2D.
Okay.
So this is the detector
Maybe a better plane.
and this is your object.
Maybe.
And you can divide this into small voxels.
So that's your actual object,
That's my actual object. Now, if your scattering happens here,
right?
so you get your scattering point inside this 3D voxel.
Right.
Okay. So that is also possible. You can reconstruct.
Okay, so from all these paths, you can reconstruct that
Because
where it's scattered.
actually, we're working on this because this is more computation intensive. So that is why it's taking it produces a large set of data. So for the time being, we collapse the full thing on a 2D plane and just work with the simple pixels on 2D pixels. That is the approach right now.
And is there any way to completely shield something from muons? Like if you put lead, then you are so something like lead, then
You may have to go to the underground because the rocks or the soil that will prevent. That's why the underground experiments, this say neutron experiments, etc., which are preferred underground.
Now, I was thinking
Just
that when
the
someone is
background.
putting a detector, one may want to sort of shield it from the other directions or something like that. But that is not really relevant.
Okay, that will not, because the muon will pass through. If there is no matter on the path of the
Then it will
muon,
just
it won't produce any interaction or something. It will just pass through.
But you also need few hundred meters of lead to block completely possible.
few hundred meters.
Yes.
No, I
that
was
is pretty-
thinking that let's say you have some object and you are putting a detector, but I mean I understand that nothing will come from underground because it's a lot of art, but I mean something can come from other directions where your object is not there, but there is some opening or something
Yes.
like that. Is that
For
possible?
this case, the muons are also coming from here, but it will just pass through.
Pass through the detector also. But
Yes, it can go through this detector. Okay, this muon will go through this detector. But since this detector is tagged with this one, there is no signal in this detector, but only one. In that case, we will
so it will just stand
It will
Depends upon
discard
the-
that thing.
because otherwise it can confuse between a scattered muon and some strain.
You have to put constraints on the experiments.
You see those layers have three layers, top 3 layers.
Yes,
bottom.
so that gives you direction.
You have the timestamp.
Right.
Yes, yes.
Because I'm sure also this is affected by some of this, all these detectors are affected by cosmic rays also probably. So that also has to be seen there. Any charged particles or cosmic ray particles will be sort of
Produce some
discarded or
signals.
something.
Also, they're affected by the, ambient
The
temperature,
acid
pressure, etc. These are also the factors. For field application, these are really the issues which you have to address actually.
For bricks,